Okay, welcome to our next Ivan workshop on a quantum-inspired NMR radio frequency for digital health with Dr. Awajagobi and Dr. Dada. At this time, I would like to introduce Dr. Awajagobi.
Good morning, good afternoon, everybody. My name is Awajagobi Omotayo Bamidele, and my colleagues is Dr. Dada Michael. We are presenting to Ivan NMR Research Group this afternoon. That's a Tuesday, October 28, 2025. The title of our presentation is A Quantum-Inspired NMR Radio Frequency for Digital Earth. Well, we are from Department of Physics, Federal University of Technology, Mina, Niger State, Nigeria. Well, I will need to give the background, and Dr. Dada will really present the rest. Since we are talking about quantum, we may need to start from atom. We all know that understanding the behavior of individual atoms in a molecule is a complex problem because all the different electrons in an atom are interacting with one another. There are some complex problems that we do not know how to solve with classical computing at any scale. Yes, but fortunately, the real world runs on quantum physics. Therefore, computational methods that make calculations by using quantum concept should in any situation and many situations be our best tool for understanding the real world around us. I want to state that no computational concept, again I repeat, no computational concept has the working memory to handle all the possible permutations of molecular behavior by using any known method. We do not have a good way to create these computational spaces with classical mechanisms, which limit their usefulness without quantum computation. In this meeting, we will discuss practical ways that computational MRI can provide innovative, data-driven solutions for the prediction, simplification, and characterization of any tissue, as well as delineating their intrinsic mechanism using quantum mechanical algorithm. And this is based on a second-order time-dependent differential equation that is shown on slide 2. Slide 2. That is the second-order differential equation that is shown on slide 2. We can see that on the slide 2. Yes. And in this slide 2, we can see equation 1. Since a very beautiful equation there, this equation is having most important MRI parameters. We have the T1 relaxation time, we have the T2 relaxation time, and also we have the radio frequency, NMR radio frequency in both the right-hand side and left-hand side of equation 1. And we can see that the transverse magnetization, or the signal, is being controlled by the radio frequency force. So as we have in equation 1, which is a general second-order differential equation with constant coefficient, was presented officially in a PhD thesis in 1997. That is presented by Awajagobi Omotayo Bamidele. And actually, this is derived from the Bloch NMR equation and can be applied to any fluid flow system at any given time t, at any point, we can obtain information about the system, provided that appropriate boundary conditions are applied to equation 1. We can also show that from equation 1, we have obtained the wave equation and solved them analytically in terms of NMR parameters by the application of appropriate initial and boundary conditions. Hence, we could get very important information about the system of any tissue, yes, based on equation 1. It should be also noted that the time in the right-hand side of that equation, that is the radio frequency term, which we are going to call the forcing function or disturbance of the system or of the equation, where M naught is the equilibrium magnetization. Yes. And if the function at the right-hand side of that equation is 0, therefore, there is no disturbance at all, and the system is undergoing freely vibrating system. Yes. But if the right-hand side is not equal to 0, or is not even close to 0, then the system is undergoing forced vibration. We can see how important equation 1 is. That is, it can be used to describe any biological system, whether freely vibrating or is undergoing forced vibration. Yes, brain tissue diagnosis can be performed, therefore, based on the availability of relaxometry data and simple computer program proficiency, which we have provided to. These programs are easy to use, highly interactive, and the data processing is fast and unambiguous at all. So the results have been used here to produce data-driven predictions that lead to the application of artificial intelligence, that is AI, and machine learning in NMR, MRI development. This application may raise opportunity for the development of new diagnosis and treatment tools for tissue management, specifically cancer care. Yes, many challenges can be addressed in the development of consistent, suitable, safe, flexible, and real-time healthcare system based on the information that is presented in this meeting and based on equation 1. The radio frequency that we have really defined controls the transverse magnetization and the signals and are obtained from the Bloch equation that is defined in equation 1. And this RFA1 feed conform a significant component of the Internet of Things, IoT concept, as shown in slide 3. So we can now see as a workflow, present a workflow radiomics in neuro-oncology and their relationship to the Bloch NMR flow equation and the RF excitation. So in slide 3 specifically, we can have 3 steps in that flow, in that workflow. 3 steps are defined. The first one is pre-processing steps and multimodal MR images where they are segmented. Then in step 2, it talks about feature extractions with the use of variety of different techniques. So that is step 2, the second step. And step 3 there, that is the third step, is a machine learning methods are then trained on the features to generate models of underlying molecular markers and predict the survival. So then, deep learning models can be used for performing each of the described steps individually or in a more comprehensive fashion. Some of these computational results, based on equation 1, as we have described, have already been applied for detailed analysis of brain tissues and neuro-oncology, as published by our research team, so that we can show the power of equation 1. Then the first one is the computational molecular magnetic resonance imaging for neuro-oncology, published in 2021. And the second one is digital molecular magnetic imaging, published in 2024. Presently, further application of this concept is being pursued and investigated in the development of quantum computing and innovative artificial intelligence, that is QAI algorithm, making magnetic resonance image diagnosis much easier. So by the time we combine quantum computing with artificial intelligence, then we are going to have a computational revolution that will really change the way we really obtain or analyze our data. So as quantum gradually emerges, that is quantum AI, is gradually emerging, we can expect significant improvement in the speed, in the efficiency, and accuracy of NMR MRI. We should also anticipate the emergence of completely new and surprising medical capabilities. As we peer into the quantum horizon in NMR MRI, our research team is therefore formally presenting a new quantum computing initiative to IVAN NMR user group with the goal of inspiring a versatile and agile NMR community. Quantum computing has emerged as a transformative force, promising to redefine the boundaries of computations to provide a much needed home base and also future meetings for promoting quantum computing in NMR, MRI, ensuring an open future for quantum computing. This is crucial and requires immediate action, possibly by IVAN user group. We have to really thank very much. We thank gratefully that the IVAN users group has given us the opportunity to make this presentation to this very important and innovative audience. The next part of the presentation will be given by Dr. Dada Michael. I now invite Dr. Dada Michael.
Thank you so much. Good morning, good afternoon, good evening, everyone. Thank you for the opportunity to make this presentation. And I would like to appreciate Professor Aojoyegbe for that introduction. Thank you so much. Like he mentioned, quantum-inspired NMR is a new concept. So why is this important? I will start with some background information about who we are. So our team is from Nigeria, as you can see, and this is the region in the country in which we are located. This is the city of Minna, so in which our university, Federal University of Technology, is located. So these are the important places, as you can see on the picture. This is our university, and as you can see, on the right-hand side, this is our faculty, in which we have the Department of Physics, in which we have the computational NMR group. So digital health is basically the use of technologies in order to improve healthcare delivery. So in recent time, we are moving from mainstream healthcare delivery into personalized healthcare. So we have cases of diseases that have to be tailored to specific regions, specific people. For instance, like within the continent, we are plagued with a problem of sickle cell disease, a disease that is not very common in other regions of the world. So if you have treatment methodologies, so each of these methodologies have to take into consideration the regions and the specific cases that are witnessed in those areas. Okay, for instance, like in the case of Nigeria, we have few MRI scanners. So we have up to like about 2,000 to 5,000 people to one scanner. So, and we have cases in which these are wards in which you have up to a million people to one scanner. So obviously, the scanning opportunity will not get to everyone because there's no way one particular scanner can get to everyone. So, which is the first part of the problem. The second part of the problem is that we have low field scanners, most of which are 0.3 Teslas, 0.35. Some of them are 0.5 Teslas. We only have few, probably less than 20 in the entire country of about 240 million people. So we have about 21.5 Teslas. And I'm not sure, I think we have like 1 or 2, 3 Tesla in the entire country. So the available scanners are not enough to go around the population. And even out of these available scanners, we have few existing spectrometers. So in most labs, most hospitals within the country, we do not have MRI. I mean MRIs at all. We don't have spectroscopy at all. So you can only take a scan. So if you want to do molecular imaging, go to the molecular level. This is actually very difficult for our population. Then secondly, most of these scanners that are available that are unable to do spectroscopy are also clinical scanners. So majority of which are only available for use in the hospital. We do not have research scanners. So maybe in the entire country, we only have like 1 or 2 research scanners, which are not are good enough for us to perform any kind of research-based MRI or NMR, so to say. So now this is the reason why our work was initiated in order to address this gap. So we do not have, our institutions are not well funded by the government. So we do not have the means to acquire these scanners. So what we looked at ways in which we can address this problem using computational means. So fortunately, the advancement in AI and machine learning has really helped us in order to now bring these computational methods into life. Please, so MRS is MRI acquisition analysis technique that measure tissue metabolite as well as the spectra in order to perform non-invasive biomolecular imaging. So you have biochemical information that are very necessary both for anatomical MRI and for diagnostic MRI. So in terms of digital health and in clinical research, we can use MRIs for neuro-oncology, epilepsy, metabolic disorders such as psychiatry, monitoring neurotransmitter or possible metabolic changes in neurological disorders. Then the fourth one is cancer out of the brain. Now, fortunately, with time, we may be able to do within the brain. I'm going to explain why we are able to do this. So now we have current classical MRS method. So they have performed quite well. So for instance, we now can do non-invasive metabolic quantification, robust spectral fitting, spectral editing techniques, high field gains and resolution improvement, multivocal imaging, so advanced pre-processing and artifact correction, parametric and subspace method for improved estimation, Bayesian and statistical uncertainty quantification, sequence and acquisition optimization. Then we can do faster and more robust clinical pipelines and reproducibility. Now, there's something that is really very important that we are now looking into is the NMR signal. So what is the source of the NMR signal? So in a typical Bloch formalism, we know that the transverse magnetization which quantifies the signal is what we call macroscopic magnetization. So which means that it's a contribution from several spins. So now the spins are quantum mechanical particles. So when we want to do our Bloch formulation, we tend to bring together all the contribution for several spins. Now, the question now is that can we look at each individual contribution? So we now have quantum mechanical processes contributing into macroscopic description of magnetic resonance. So can we look at the quantum mechanical basis of these signals by considering contribution from each of the spin? So we now say that, okay, deep down, NMR may probably be a quantum mechanical phenomenon. So can we look at the quantum mechanical basis of these signals so that we can look at what these contributions look like at the onset of the disease? So with the advancement in AI and machine learning, we may be able to study some of these behaviors at the molecular level, and we may now in time be able to make prediction as to the kind of behavior in some of these magnetic spins that leads to diseases. So if we are able to nip this onset at the right time, we may be able to treat diseases better. So, and that's the reason why we say that quantum computing is offering us not just one opportunity, it's offering us two opportunities. One, we have a way in which we can look at the diseases at the molecular level and look at ways in which we can treat them as soon as possible. Then secondly, we can use quantum mechanical methods in terms of quantum machine learning to train our algorithm better. Actually, we are currently working on some projects that has to do with using quantum machine learning for image segmentation and image classification. So, and we found out that these methods are so important in the sense that the more data you have for quantum machine learning models, the more robust your models become. So now, in our own case, we do not have access to a lot of GPUs. So training classical machine learning models is quite difficult for us, because by the time you have a very large data set, then your model becomes so difficult to train. So, but we now discover that quantum machine learning can help us to train a more robust algorithm, no matter the amount of data that is available. So we now see the opportunity that quantum processes offer to us in terms of digital health. So what are the current challenges of classical MRS? So we have talked about how important or the achievement that classical MRS has. So now what are the challenges? So we have a low signal to noise ratio. So this is really very important when we are considering relevant metabolite that are not strong enough in comparison to the noise. So then we talk about the peak overlap and J coupling, then short acquisition and limited resolution. This is a very big problem. So because when we do not have the appropriate resolution, we may not be able to see what we plan to see in terms of disease development, or when we wish to monitor the effectiveness of a particular treatment plan. So especially the one that has to do with drugs. So we now have quantum drugs now. So now We also have what we call model mismatch and broad background. So this has to do with baseline drift. We know that macromolecules and imperfect water suppression can really create biases. Then we have what we call non-convex optimization and local minima. Then we have scalability for MRSI. So in conjunction with multivocel data set. So now, most times this is very, very pronounced when you have water molecules, since the MR signal from the water molecules tend to be very high because of the proton content. So they tend to suppress some other signals from some other vocels. So now we need to say, okay, how do we optimize in order for us to be able to suppress the signals that we do not want? So then number 7, we have uncertainty quantification. So this is actually very difficult in classical methods. So now the question now is that how can quantum inspired methods help? So in what ways can quantum inspired methods solve the problems we just highlighted? So now we just give like an idea that, okay, in terms of low signal to noise ratio, we can perform what we call structure low rank denoising using the Anke SVD, tensor train, and some other methods. Also, in terms of the overlapping peaks and J coupling, yes, we can use tensor networks correlation parameterization, so and be able to overcome this challenge. Then the third one is short acquisition, limited spectral resolution. So now, quantum inspired method can help us when we apply something like a subspace super resolution. So coupled with variational refinement. So when we apply the denoising, we can see how we can reduce the background noise to the barest minimum, and we can highlight those particular regions of the signal that we expect to see. Then, in terms of model mismatch and broad baselines, we can use what we call flexible latent models, such as structure priors, in order to address the problem. Then, for local minima poor convergence, then we can use quantum annealing methods. So now there are a lot of them that are currently being explored for several medical imaging applications. Then we have scalability to MRSI. So we can use joint tensorization and TT compression across vocels. So this will help us to compress spatial and spectral structure, and also denoise jointly and share information across the vocels. Then uncertainty codification using a variational base bootstrap over structure pipeline can be used to address this problem. Then finally, avoiding overfitting while exploiting weak structure. So now we can actually find ways in which we can improve our models while we perform low rank regularization, compact parameterization. So this promotes global simplicity and prevents spurious small peaks from fitting noise while we allow really small signals and support it across structure. So now this is the basis. So quantum inspired method, what is the basic physics? So as you can see, this is our Bloch equation. So in the Bloch equation, M is our magnetization factor, which is actually a macroscopic term. So macroscopic term in which we have a summation, like a combination of several quantum mechanical contribution to the magnetization. So now, in order for us to have like a typical MRI signal, we need to make sure that Lamont condition is maintained, so which is given by the second equation here. So now the Lamont frequency can be tuned to any of these signals. We notice that there is actually something that goes on at the quantum mechanical level. So because of time, I will not be able to explain further. All right. So now quantum inspired method. So this is the chemical shift conversion. So the chemical shift in ppm are converted to frequency offset according to this equation. So we can see that this is the frequency offset. This is metabolite chemical shift and the reference chemical shift. So which we know, we already know this for water. So now, how do we start? Then we start from signal model based on the Bloch solution. So I don't want to take too much of our time. The transfer magnetization is expressed at the first equation there. So that first equation is basically the source of our MRI signal. So now from this MRI signal, we can actually compute our free induction decay, the FID. So the FID is given by the second equation. And as you can see in the second equation, there's a summation sign in front of the A subscript M there. So which shows what we have been talking about all along. So that summation is actually indicative of the fact that there are components from each individual quantum mechanical spin to our free induction decay. So all the terms are defined. Then we talk about the estimation from the Bloch decay. So and the Bloch decay is actually quite very interesting because we see that T2 is actually very, very sensitive to spin-spin interaction. So in the cases where you have disease or some other tissues, so you have a particular molecule that is actually not behaving the way it's supposed to behave. They are interacting with their environment. The interaction within the environment is always reflected on the T2 decay. So when we are able to monitor the T2 decay, we may be able to monitor both diseases at both classical and quantum mechanical levels. So now, these are the quantum inspired feature extraction that we did with Bloch physics. So we see that each of these are quantum mechanical terms that we have brought out in order for us to do what we call feature extraction, similar to the way in which our data is prepared for machine learning. So we have what we call quantum Fourier transform of Bloch signal, which is actually very interesting. It's an area of serious research currently. So we talk about the QFT implementation. So these can actually be used for us to get our quantum mechanical based Fourier transform signal. So we talk about the spectral feature from the Bloch equation, which computes the spectral entropy, the energy ratio. Then the quantum statistical features, we computed the skewness and the kurtosis. Then we talk about the phase uniformity from the Bloch's precision. So this is actually very, very important in the sense that, classically speaking, we are told that the spin move from the low energy state to the high energy state, but quantum mechanically speaking, this is not true. So what happens? We have precision that moves right from the ground state energy up to the excited state in the presence of B1 magnetic field. So now, why the rotation is going on even at the excited state. So by the time the B1 field is removed, it still relaxes back. So both T1 and T2 are computed from that relaxation. So we also talk about the quantum entanglement metrics for multi-spin system. So now, one challenge that we always mention when it comes to addressing quantum mechanical based method is that if we are to consider just one spin, so what use is it in clinical diagnosis? Because there are to be interaction in order for it to be so important for real-time diagnosis. So this is really very important, the quantum entanglement metrics, so that you can bring in together several spins that are interacting and we'll be able to get so many features from them. Then we talk about entanglement entropy for coupled spins. For instance, in the case of metastatic cells, we notice that each of the cancer cells are quite synonymous, so to say, to the tissue in which the cancer cells are found. So, which means that they take over some features from the immediate environment in order for them to metastatize. So, which means that the interaction is going to be very important, and we can consider that as a coupled spin system. So we talk about the quantum coherence analysis with Bloch parameters. So, which is basically has to do with the direct T2 star estimation from Bloch decay. So now, in terms of integrating the Bloch equation into quantum machine learning, so it's one side to say, okay, this process is basically quantum mechanical. Then we can use the so-called method in order for us to integrate our method into real-time machine learning method. So all we need to do, so I would have loved to explain this, but so that we don't waste too much of our time. Then this is basically block-based quantum features transformation. So we do what we call phase encoding of blocks precision. So real-time imaginary concatenation of block solutions. So quantum classification with block-derived features, then quantum regression for metabolite quantification. Then we talk about the block-based metabolite quantification. Then we can see that from here, the metabolite that we've always assessed, that we can now assess them at a different level from what we used to do before. Like we need to consider them in their immediate environment, which is quantum mechanical, so to say. So it's their immediate environment. We can see features at that quantum mechanical level that may be different from what we have observed at the macroscopy level. So now, after training the model, these are the results. We have quite enough of them. So what we did is we developed an algorithm that compute the FID. So using just 200 points just for this research. Then we kind of look at what we call quantum feature importance. So what quantum feature are actually very important or contributing the most to this signal. So now, so what we did is that we got some clinical data for three disease conditions compare for a normal patient. So we have a normal patient. So we took some of those data from glioma, for a patient with stroke, from a patient with Alzheimer's. So we use experimental data set for us to get this to perform this algorithm. So now, and after training the model, we trained the model for I think about 1,000 epochs. So and we were able to get what we call the classical spectrum. So we still have issues in terms of interpreting quantum features based on what we know as the nature of quantum mechanics. So when we compute what we call the wave function, we said the wave function does not have a meaning, but when we do the probability function, we kind of have what we call, okay, it has the meaning, so we can know the location of a quantum mechanical particle. So for now, we are going to use this feature for us to train and get our classical spectrum that can be used for real-time diagnosis. And as you can see, this is the intensity as versus the chemical shift. So showing each of these results. So we were able to develop a computer application that can be tried, that can be tested from this work. So I would have loved to show them, but it's kind of making the system run slow. So if I had to show them, it may take us like maybe like 10 minutes before it comes up. So where we can specify the data that you are going to train your model with, then you perform your model training on that particular data set in order for you to get the classical spectrum that is quantum inspired. So I think basically we will be able to incorporate the whole essence of quantum method into magnetic resonance spectroscopy, yes, and clinical diagnosis towards the use in digital health. So this is our head of unit, Professor Awojo Yogbe, and this is a cross section of our team members, so which are currently being trained in the lab. So we have quite a lot of them that could not feature in the picture. So we hope that in future presentation we'll be able to introduce them to the to us.
Okay, do we have any questions from the audience? Well, thank you, Dr. Dada and Dr. Awajobi, for your presentations, and for participating with Ivan. Do you have any questions or comments that you'd like to make beyond what you've already said? Okay, well, if there's no questions, then again, I would like to thank Dr. Dada and Dr. Awajobi, and I think we'll go ahead and end the meeting then now.
Thank you very much.
Thank you.
Thank you so much.
Thank you.
Yeah.
Have a good day.
Thank you.
Bye.
So, one key.